Introduction to AVL Trees. Hello everyone, we're going to look at important tree data structure, which is the AVL tree. First, let's briefly talk about binary search trees or BSTs because these are trees where each node has at most two children, with the left child having a smaller value and the right child having a larger value than their parent node. So with binary search tree in mind, AVL trees are, you can think of them as a special kind of binary search tree. AVL trees are self-balancing, which means no matter how many nodes you add or remove, the tree reorganizes itself to ensure that the height stays logarithmic in relation to the number of nodes. This guarantees efficient operations. So the AVL tree is named after its inventors, Adelson, Belsky, and Landis, who introduced it in 1962. This structure is fundamental if you need fast retrieval, insertion, and deletion. Properties of AVL keys. So the key to an AVL tree's efficiency is its balance. So each node in an AVL tree has a balance factor. And the way you calculate this balance factor is by calculating the height difference between its left and right subtree, and this factor must always be -1, 0, or +1. So if the balance factor of any node deviates from these values, the tree performs rotations to bring it back. This ensures that the tree remains balanced, keeping operations optimal. Regarding height, you want to remember this formula, which shows that height of a node equals 1 plus the maximum height of its left subtree and right subtree. And this calculation helps determine when rotations are needed to maintain the tree's balance. So this is a Python code example. So we have AVL tree node, and when we initialize this tree, we are storing left, right, and key, which we've seen in binary search tree. In addition to that, we are storing height, and height starts with 1 when you initialize, and we would have 3 important methods, which is update height. This is getting the height, which we talked about. It's 1 plus max get height, self left, get height of self right. So this makes us wonder how to get height. We just, if node it doesn't exist, we are returning 0, otherwise returning node's height. And then lastly, the get balance method will do the get height of the left subtree minus get height of the right subtree. Rotations to maintain balance. So AVL trees maintain balance by rotations. There are two primary types, which are single rotations and double rotations. We're going to talk more about this in a different lecture slides. So just for now, we are just doing an overview. So in a single rotation, we have the right rotation, and right rotation is also known as LL rotation, and the left rotation, uh, also known as RR rotation. These are used when the tree is heavily skewed in one direction. Double rotations are slightly more complex, and they involve two-step processes. The left-right and right-left rotations correct cases where a single rotation wouldn't suffice, and these rotations, they are crucial for maintaining the strict balance of an AVL tree. Insertion in AVL trees. So inserting a node into an AVL tree starts by following the standard binary search tree insertion process. The difference is after inserting, you want to traverse back up the tree, updating heights and checking balance factor. And if you find that there is a violation in a balance factor, you want to apply appropriate rotations. It can be either single or double, and they are performed to restore balance. And this ensures that our tree remains efficient in terms of height and access times. Deletion in AVL trees. So deletion in an AVL tree is more complex than insertion. So after deleting a node, similar to insertion, you need to check and adjust the balance of the tree as you move up. And this might involve multiple rotations to ensure that trees remain balanced. This is complex, but these steps are important for maintaining the best performance of AVL trees across all operations. Searching in AVL trees. Searching in an AVL tree is identical to searching in any binary search tree. You would begin at the root and traverse down the tree, choosing the left or right branches based on comparison with current node values. And unlike regular binary search tree, thanks to the balancing of AVL trees, this search operation remains efficient. It will always operate in O log n time. Time and space complexities. So the operation of insertion, deletion, and search in an AVL tree all have a time complexity of O log n. And this efficiency is due to the tree's balanced nature. For space complexity, it primarily involves storing the nodes themselves and the balance vectors. But overall, it is linear with respect to the number of nodes and the tree. Applications of AVL trees. So AVL trees are used in applications where quick data retrieval is crucial. This includes database indexing to speed up query processing and memory management systems. AVL trees are often compared to other data structures like red-black trees and B trees, each having its own use case depending on the specific needs of an application. Conclusion, this concludes introduction to AVL trees. Its AVL tree is a fascinating tree, and I definitely encourage you to look into this further and also do some additional practice. Thank you everyone for listening.